Summary of lecture 24. This is on the Fourier series, and this is the second part. I have discussed the first three, the summary from the book, and now let's discuss about the summary from the lecture. And they are pretty connected, I would say, of course. Let me bring out important concept from last lecture is that remember that cos x and sin x are perpendicular in the function space. And again, function space is that just we meant that instead of having vector now in our vector space, now we are having a function, which is the f in our function space. So like the function behaving the same way as the vector, okay? Now let's discuss the first thing about orthonormal basis, okay? So suppose I'm in my n time by n, I have n by n matrix here, and then I have, so this is orthogonal matrix, and the orthogonal matrix by definition I have all the orthonormal vector, okay? So all these are orthonormal vector. Or I should say I can use them as bases, right? Or bases. Okay. So I can construct a vector that lives inside this vector space using all those bases, right? So I would say some combination of x1, some combination of q2, some combination of q1, q2, and some combination of until qn. And this is also, let's say we are having the same idea of what we have learned in the first part, which is infinite. Okay, so infinitely long. So we also have an orthonormal basis that are infinitely long. So we want to define a vector there using all of these bases. Okay, we have that already. And then the question is, how do you get this constant, this coefficient number x1? Okay, I'll just give you the answer right away because it's pretty clear that we can use the property, the nice property of orthogonality, which are the qi times qj will be 0, right? The dot product of them. So I'll just multiply everything with q1. So v dotted with the q1, right? And then this is x1, q1 also dotted with q1. And then my x2, q2 dotted with q1 until xn, q1 dotted with qn, okay? And I had a lot of zeros here because all of this will be zeros, right? Remember, qi dotted with qj equals 0 because these two are perpendicular, you know, they are orthogonal, okay? Perpendicular, orthogonal, same thing, tomato, tomato, okay? And I just want to create this in another syntax, another way to write. So the dotted means the transpose, and this is also q1 transpose q1, right? And there you have it. I have it already. I have my x1, which is the q1 transpose v. That's it. Where does this term go? Well, q1 transpose q1 is the vector length of q1, and since we have orthonormality on both one, then we just equal 1. So that doesn't matter, and we have this formula for coefficient x1, right? And then just to see it in another way, let's see this formula in another way, okay? And then you can express this in terms of vector, right? So you have those vector q here that have all that orthonormal basis. And you have that vector x here, which consists of this also infinitely long x that live in Rn. So you have this v equal q times x, and then what is x? Exactly, you can inverse it and then v, okay? But then you can also use the property of the orthogonal matrix. So the q inverse will be equal to q transpose v x, okay? And now actually this is saying the same thing as this, just this one expressing it in terms of matrix, right? So if you see it clearly here, the x1 term will be that the q1 transpose term times the v, the whole v, right? Which is exactly what we have here. Okay, so that's about the orthogonality. And this will be the building blocks. Will be the way we build our Fourier series. This is the property of the orthogonality that we will see later on in the Fourier series. Let me clear up some space. Let's continue. Now we are interested in the Fourier series. Okay, now let's define what is Fourier series. It's a function of x which expressed as cos of 0x, cos sine of 0x, plus cos of 1x, plus sin of 1x, plus cos of 2x, and I hope you get the idea until cos of nx plus sin nx, okay? So kind of a function that tells you how many components of each harmonic, each cos x and sin x play a part in that function. And of course we have the coefficient also. So in this case, if you remember the functions of like cos x is a function of this wavelength, and then the coefficient here which will tell you about the amplitude. So we have, for example, here our a1, a2. Let's have a different letter here. For sine x, let's use b1, and then for cos 2x, a2, for sine b2, okay? And actually the cos 0 will be 1, right? And sin 0 will be 0. So the Fourier series is simply, well, if we just simplify this, then we have the a0 times a1 cos x plus b1 sine x plus a2 cos 2x plus b2 sine 2x until the n term, okay, and x something. So I will delete that, but I think this is pretty informative for me, because I always thought that there is some constant here. I don't know where does this come from, but now I know that this comes from this cos of 0x here, which is this one, and then sin 0x just gone here, and then you just plug in the coefficient here, the a0, okay? I will emphasize this one. So this is the Fourier series, right? Fourier, if I can just spell correctly, why it is so hard to spell sometimes. Fourier series, right? Okay. Now, similarly to the orthogonal and how we express a vector in terms of the orthogonal basis, orthonormal basis, we are interested now in finding the coefficient. Now a0 is pretty simple. It doesn't have any functions that precede it. It doesn't have a cos x, sin x here. So let's find a1. Okay, so what is a1? Now, similarly to the idea of orthogonality, and I also introduced to you before that the cos x and sin x are orthogonal in function space, so that's what we will do. Now, before moving further, I just want to put the Q into here so that it can help you see like the comparison between the vector space and the function space. So what we used to have here as our basis, our orthonormal basis here, we now have those bases. Now we have a function, okay, here, which is, well, personally, it is kind of confusing for me because this is scalar, right? Each component of Q it's not a scalar, it's some vector. Each vector, you know, it's column here, but each point is a scalar. But now we have this function that has continuous functions of cos x that just keeps going into the infinite, and then all the bases has that infinitely long also to the n component. So just stare at it and then let it sink into your head. So from Q1, so our basis now is cos x, sin x, cos 2x, sin 2x until cos nx and sin nx. Okay. Now we learned from previous part about this notation, right? That the inner product of two functions are, well, the integration of them. We integrate fx and gx. And let's do the exact same thing. So now let's introduce our gx is cos x, because we're interested in a1 again, so we want to keep this part alive and we want to make them all goes to 0, right? So on the right hand side we have this fx times gx, which is just the integration from 0 to 2 pi. Remember 2 pi because here we're all interested in cos x and sin x, and they're just keep repeating fx. Remember this fx plus 2 pi. I'll just write it here, okay. Of fx, let's continue our right hand side, and cos x of dx. Okay, and then our left hand side we will have all these terms actually. Okay, so a0 cos x dx times the integral of a1 cos x squared dx times integral of b1 sin x cos x dx, and so on. Okay, and of course the constant can go out. a1 b1, right? But then, okay, this is where the orthogonality comes in, that sin x and cos x are orthogonal, therefore their length are 1. And you can actually use the trigonometry identity and prove it yourself here. So we have a bunch of 0, a lot of 0 here. So this goes to 0, 0, and everything goes to 0. And we only left off with this one, this term. And actually the cos x dx from 0 to 2 pi is also 0. Well, this one I can prove really quickly because the integration of them is sin x. And then we go from 2 pi and 0. Sin 2x is 0 minus 0, therefore 0. This also goes to 0. And so I will delete that, everything. So we only have this term of a1 to 2 pi cos x squared dx, which is also equal to this form. Okay, and with some trigonometry magic we have pi of a1. So now we bring this up together. So a1 pi, right? 0 to pi fx cos x dx. And we have our pi, our a1. And this is our Fourier coefficient of a1. Then we can do the same thing, follow the same process with the b1 until bn or an. And the lecture ends there. So there's this idea of moving the vector space to the function space, but using the same principle. They behave the same thing, that just right now we have these functions as our basis instead of the columns. And this helps us in computing the Fourier coefficient for Fourier series. That's it. Thank you.